You've heard Andromeda is about 200,000 light-years wide. In this video, we're going to blow that number up and show you a galaxy so layered and huge that the word big just stops working. You probably think big means something simple, like how wide is it from one edge to the other? That works for a table, a car, even a planet. But for a galaxy, that question quietly breaks. In astronomy, there is no sharp wall where a galaxy stops. The stars thin out, the gas thins out, the dark matter thins out, but nothing just cuts off. So when you ask how big is Andromeda, what you are really doing is choosing where to stop counting, even if you do not realize you're making that choice. So what is the wrong part of the question you have been asking this whole time? You are treating edge as if it is a physical object, when it is actually a human decision. The bright central region of Andromeda looks clear in a photograph, but if you keep going outward, the stars just get fewer and fainter. At some point your detector says, "I cannot see anymore," and that is where most people stop. But that stop line is not in the galaxy, it is in your instrument. If you build a better camera, expose for longer, push the noise level down, suddenly Andromeda grows. The galaxy did not change overnight. Your definition did. So if edge is not real, and the galaxy just fades, what are astronomers actually measuring when they write down a size for Andromeda? In practice, they talk about several different sizes, all referring to the same object, and each one tells you something different. First, there is the stellar disk, the main bright disk of stars. Depending on how faint you allow the starlight to be before you stop counting, that disk is roughly between 150,000 and 260,000 light-years across. In metric, that is on the order of 1.5 to about 2.5 quintillion kilometers, a 1 followed by 18 zeros. If you use the Earth-Sun distance as a yardstick, which is about 150 million kilometers, you are talking around 10 million to 15 million of those lined up in a row. In miles, you're in the range of almost a trillion miles. It is already huge, and that is just the bright disk. Then there is the gas disk, mainly neutral hydrogen picked up by radio telescopes. This gas is not limited to the same region as the bright stars. It reaches further out in a kind of extended low-density layer around the disk. If you define size based on where this gas is still clearly detected, Andromeda gets larger again. You now have a galaxy where the visible part you're used to seeing in photos is just the inner section of a bigger structure. And then you step into the most extreme definition, the dark matter halo. Most of Andromeda's mass is not visible at all. It sits in this huge, roughly spherical cloud of dark matter, detected only through its gravity. That halo can extend out to something like a few 100,000 parsecs, which is roughly 1 million light-years in diameter. In kilometers, that is on the order of 10 to the power of 22 kilometers. At that scale, miles are only useful as a comparison word. Millions of trillions of miles, not as a precise tool. So depending on whether you mean the bright stars, the gas, or the dark matter, you can honestly say Andromeda is a couple 100,000 light-years wide, or closer to 1 million. If we have all these measurements, why can't we agree on one final number and be done with it? Because every one of those sizes comes from a rule, and the rule is not unique. To define a diameter, you must set a threshold. You might say, count all stars brighter than this level, and stop once the surface brightness drops below that. Or follow the gas until the density falls below that value. Change the brightness limit or the density limit, and the diameter shifts. This is not a math trick, it is built into the way galaxies work. They do not give you an automatic border, you enforce one. You can see the problem clearly when you look at deeper and deeper images of Andromeda. Take a shallow exposure, you get a compact bright disk. Take a longer exposure, and faint extensions appear. Push even deeper with the big telescopes, and you see streams of stars, shells and low surface brightness fluff much further out. Every jump in sensitivity pushes your edge further away. The galaxy did not grow, your ruler did. That is why in the scientific literature you will see several radii quoted. each one tied to a specific brightness or density rule. So if everything depends on detection limits and arbitrary thresholds, why is Andromeda such a focus of all these size arguments in the first place? Because its distance puts it in a sweet spot. Andromeda is about 2.5 million light-years away from you. In kilometers, that is roughly 2.4 times 10 to the power of 19. In miles, about 1.5 times 10 to the power of 19. That is close on a cosmic scale. At that distance, big ground-based telescopes and space telescopes can actually resolve individual stars in many parts of the galaxy. We can see star clusters, red giants in the halo, and detailed structures in the disk. At the same time, with modern wide-field cameras, you can still capture the entire galaxy, from end to end, in a single image. Most galaxies do not give you that combination. If they are much farther away, their stars blur together and you are stuck with a smooth patch of light. If they are much closer, they spill across the sky so much that it is hard to treat them as one object in a single frame. Andromeda sits right in the zone where we can test what size means, starting from the compact central bulge, through the disk, out into faint tidal streams in the halo, and still think of it as one system. That makes it the main laboratory for turning a fuzzy question like, how big is a galaxy, into a set of concrete, testable definitions. After all that work, do we ever get to say one clean number when someone asks, so how big is it? The honest answer is no, not if you want to stay honest. What you end up with is a small set of different Andromeda sizes, each one linked to a different physical idea. You have the bright Andromeda defined by the stellar disk, roughly 150,000 to 260,000 light-years across. You have the gas-rich Andromeda, where neutral hydrogen and other gas extend further out than the stars. You have the halo Andromeda, traced by scattered stars and streams left over from smaller galaxies it has torn apart. And finally, you have the dark matter Andromeda, the full halo that dominates the gravity and may reach out to roughly 1 million light-years. None of these is fake. They all describe the same galaxy, just with different priorities. One cares about light you can see, one cares about where gas is still present, one cares about where stars and streams still show the galaxy's influence. One cares purely about gravity. So when you ask, how big is Andromeda? The real question becomes, big in which sense? Light, gas, stars, or gravity? And if all of that already stretches your sense of scale, what happens when you find out the hat, on the sky above your head, this too big to define galaxy, actually covers a patch larger than the full moon, even from 2.5 million light-years away? How can something that looks like a tiny blur over your head actually be bigger than the full moon in your sky? When most people hear Andromeda, they think of a small smudge in a telescope, a little hazy patch that barely covers anything. But if your eyes were as sensitive as a good camera, that idea would collapse. Andromeda's bright main body stretches across about 3 degrees of sky. The full moon is about half a degree, so you're talking roughly 6 moon widths side by side. If you hold your fist out at arm's length, Andromeda is big enough to swallow that whole area and more. The only reason you don't experience it that way is that your eyes don't collect enough light fast enough. So you're walking under a galaxy that in angular size beats the moon, and your brain files it as tiny fuzz. So what does that 3 degrees actually mean in physical terms once you connect it to real distances? An angle on the sky by itself doesn't give you size. A small nearby object and a huge distant object can take up the same angle, like a coin close to your face in a building far away. To turn that 3-degree spread into a real diameter, you need the distance, which, for Andromeda, is about 2.5 million light-years. Once you have angle and distance together, simple geometry tells you the linear size. Even if you play conservative and only count a disk of around 150,000 light-years across, that already works out to roughly 1.4 times 10 to the power of 18 kilometers. In plain terms, that's about 1.5 quintillion kilometers. Now, use the Earth-Sun distance as your intuitive ruler. One astronomical unit, the distance from Earth to the Sun, is about 150 million kilometers. Andromeda's stellar disk is roughly 150 million of those Earth-Sun steps laid side by side. In miles, that's on the order of 9 times 10 to the power of 17 miles, closing in on a quintillion miles. If you took a normal car and drove at highway speed, even if you never stopped, you would not cross that disk before the universe itself runs out of usable energy. Even if you upgraded to something moving at several kilometers per second, which is already way beyond any jet, you would still need time spans that break human history. So if it's that big physically, and that big in angle, what do our telescopes actually pick up that your eyes can't? Modern wide-field instruments, from serious backyard setups to professional surveys, show Andromeda as much more than a bright oval. Amateur astrophotographers use CCD or CMOS cameras, track the sky for hours, and then stack hundreds of exposures. Professional surveys like wide-field optical and ultraviolet projects such as WFST, class telescopes and missions like Galaxy do the same thing at a higher level. They all agree on one thing: once you integrate long enough, the galaxy keeps spreading out. The luminous disk isn't a clean, sharp boundary. It grades into faint, wispy structures, low surface brightness extensions, and subtle outer arms. These faint regions are not camera noise. You can cross-check them with different instruments, different filters, different nights, and they line up. They contain real stars, real gas, real structure, and every time the hardware improves, every time the sensitivity goes up, those features can be traced further. The apparent size, in degrees on the sky, swells outward. The old edge was just the point where our detectors quietly quit. If Andromeda is sitting there that huge in your sky, why do you almost never really see it that way with your own eyes? The problem is how your visual system collects light. Your naked eye samples are light over tiny fractions of a second, and it does not stack those samples over time the way a camera can. The faint outer regions of Andromeda simply do not deliver enough photons per instant to trigger your perception as a solid thing. So what you get, under a very dark sky with no light pollution, is a small bright central bulge, and a bit of the inner disk, a compact glow. That is just a fraction of the full structure. A digital sensor works differently. A CCD or CMOS chip can sit there for minutes or hours, quietly counting every photon that arrives, frame after frame. Software can align and combine those frames so that the signal from the galaxy adds up, while random noise averages out. The result is that your brain says small fuzzy blob, but the camera, which does not get bored and does not blink, records disk plus extended arms plus faint halo, more than 6 times the moon's diameter. The galaxy has been in the same place for millions of years. Only your detector changed. So what does that do to your normal sense of what a big means? On Earth, you use kilometers and miles for big things, cities, mountains, ranges, maybe the orbit of the moon. Those numbers feel large but still manageable. You can imagine a plane flying that distance in hours or a car in days. With Andromeda's apparent size, you get a trick that helps you step out of that comfort zone. You can compare it directly to something you know very well, the moon in your sky. When you realize that this galaxy, sitting 2.5 million light-years away, actually appears larger than the moon, your normal idea of big stops being useful. At that point, big is not just a larger number, it is a complete failure of your intuitive tools. An object that distant, covering that much of the sky and spanning hundreds of thousands of light-years in physical size, doesn't fit with the way you normally think about distance and area. It feels like a glitch in your sense of scale. The only way to fix that glitch is to lock down the distance as precisely as possible, so that when you see that angle in the sky, you know exactly how far out the edges really are. So if everything about Andromeda's apparent size is already breaking your intuition, how do we actually know it is 2.5 million light-years away, and not something much smaller and closer tricking us with the same angle? How do you turn a bright patch in the sky into a real object with a real size instead of just a pretty smear of pixels? You cannot talk about how big Andromeda is until you know exactly how far away it is. An object that looks large on the sky might be small and nearby, or huge and very far. The angle you see over your head is only half the story. For Andromeda, nailing down a distance of around 765 kiloparsecs, which is about 2.5 million light-years. It's what lets you turn those 3 degrees on the sky into an actual physical diameter in light-years and kilometers. Without that distance, all those size numbers are just guesses. With it, when you say a couple 100,000 light-years across, you're talking about a calibrated measurement, not a vibe. So how do you measure 2.5 million light-years with no tape measure, no probe, nothing you can physically send there? The first big tool is a special kind of star, a Cepheid variable. These stars pulse in brightness, getting brighter and dimmer on a regular cycle. The key is that the period of that pulse, how long they take to go from bright to dim and back again, is directly linked to their true power output, their intrinsic luminosity. In metric terms, once you know the period, you can work out how many watts they're really emitting. Then you compare that to how faint they look in your telescope. If they are intrinsically very bright but look very faint, they must be far away. Andromeda was one of the first galaxies where this trick was used outside the Milky Way. In the 1920s, Edwin Hubble spotted Cepheid variables in what people then called the Andromeda Nebula. By measuring their periods and apparent brightnesses, he found distances that were way beyond the size of our own galaxy. That one calculation basically killed the idea that Andromeda was just some cloud inside the Milky Way. It was too far, too big. It had to be a separate galaxy. But Cepheids are only one step. How do you refine that distance so much that you can tell the difference between, say, a 150,000 light-year disk and a 260,000 light-year disk? Modern surveys use another tool called the tip of the red giant branch. In simple terms, red giant stars climb up in brightness as they evolve, then hit a fairly standard maximum before changing state. That tip brightness is well understood from stellar physics. Because Andromeda is close enough for large telescopes to resolve individual red giant stars in its halo and outer disk, astronomers can measure how bright the very brightest ones actually look in our sky. Compare that apparent brightness to the known true brightness, and you get distance again. The strength of this method is precision. You're not guessing at some fuzzy average. You're picking out a sharp cut-off point in the brightness distribution. That lets you pin Andromeda's distance down to within a few percent, and once your distance is that tight, the diameter you infer from its angular size is also tight. You can seriously ask whether the disk stops closer in, around 150,000 light-years, or if it stretches further out toward that 260,000 light-year range, and you're not just rolling the dice. If these methods are so good, why don't we just use the obvious ones, like parallax or redshift, that you always hear about in space videos? Parallax, the classic method, is where you watch an object shift slightly against the background as Earth moves around the Sun. It's pure geometry. The problem is that the shift gets smaller and smaller with distance. Even with very precise missions like Gaia, the practical limit is on the order of a few thousand light-years. Maybe tens of thousands, not millions. For Andromeda, the parallax angle is so tiny that it's below the noise floor. The effect is real, but current instruments can't measure it cleanly enough to give you that 765 kiloparsec distance on their own. Redshift is the other famous tool. In an expanding universe, distant galaxies have their light stretched to longer, redder wavelengths, and the amount of stretch roughly tracks distance on very large scales. But Andromeda is a bad fit for this shortcut, because it is not redshifted, it is blue shifted. Its light is shifted to slightly shorter, bluer wavelengths, because Andromeda is moving towards us, not away, at about 110 to 165 kilometers per second, around 70 to 100 miles per second. That motion comes from local gravity, not from the universe's expansion. If you tried to use that blue shift as if it were a standard redshift distance indicator, you would get pure nonsense. So if parallax is too weak and redshift is misleading, how do you know you are not building this whole story on one fragile method that could be wrong? You stack methods. Astronomers do not trust any single distance indicator on its own, especially for something as important as the nearest major galaxy. They use Cepheid variables. They use the tip of the red giant branch. They add in other techniques where they can, like surface brightness fluctuations, which look at how the granular texture of unresolved stars changes with distance, and detached eclipsing binaries where two stars orbit and eclipse each other and their properties can be modelled in detail. Each method has its own systematics, its own weaknesses, but they are different weaknesses. When all of these independent tools are applied to Andromeda, they converge on roughly the same distance, around those 765 kiloparsecs, or 2.5 million light-years. The error bars get small enough that tweaking them does not suddenly make Andromeda twice as big or half as big. It tightens the picture instead of blowing it up. So when you say Andromeda is a couple 100,000 light-years across, you're not just quoting some old textbook line, you're reading off a cosmic ruler that has been calibrated, cross-checked and beaten up by multiple methods until the numbers agree. But once you know how far away Andromeda really is, and how wide that disk truly spans, there is a new question that hits even harder. If this galaxy is that large in physical size, just how many stars are you actually talking about lighting it up from the inside? How many stars does it take before the word "a lot" stops being useful? For Andromeda, the headline number is roughly 1 trillion stars. That is a 1 with 12 zeros, around 3 to 5 times more than the Milky Way's 2 to 400 billion. So when people say Andromeda is a bigger galaxy, in terms of stars, this is what they mean. 1 trillion separate nuclear fusion reactors, scattered across something like 200,000 light-years or more of disk. If you tried to count them out loud, 1 star per second, no breaks, no sleep, you would still be counting after about 30,000 years. That is longer than all of the recorded human history, just to say the word "one" over and over again. So where does that number actually come from? Because nobody is sitting there clicking a counter on every single star. A big part of the story comes from deep images taken with the Hubble Space Telescope. Hubble has stared at patches of Andromeda's disk for long periods, collecting light from stars that are far too faint for smaller telescopes. In those deep fields, astronomers can directly resolve and measure over 200 million individual stars, and those are mostly the brighter ones, stars that are similar to the Sun or more luminous. Right away, that tells you Andromeda is packed, but that is only the visible tip of the population. Below Hubble's detection limit, there are many more low-mass, faint stars that you do not see individually. To get from hundreds of millions we see to around 1 trillion more in we think are there, astronomers build models of the stellar population. They take what they know about how stars form, how many small stars you get for each big one, how their brightness changes with age, and then they fit those models to the observed brightness distribution. When the model that best matches the data is scaled up to cover the whole galaxy, not just the fields Hubble looked at, the total count lands in that trillion range. You're not guessing wildly, you're using real detections plus well-tested physics of star formation. But 1 trillion stars scattered in a tiny ball would be a very different galaxy from 1 trillion spread out over a huge volume. So the next question is, how tightly are these stars packed, and how much space do they actually fill? Inside Andromeda, the density changes a lot from region to region. In the central bulge, that bright rounded core, the density can reach thousands of stars in a single cubic light-year. That is an insane crowding level compared to your local area. Out in the halo, far beyond the bright disk, the density may drop to just a few stars in a cubic light-year or even less. So when you ask how big is Andromeda, on the inside it turns into how much room do you need to host 1 trillion stars without the whole structure tearing itself apart. Those stars are not floating quietly either. Typical orbital speeds in the disk are around 250 kilometers per second, about 560,000 miles per hour. At those speeds, a star at a moderate radius might complete one orbit around the galaxy in a few 100 million years. Over the lifetime of the universe, that means only a handful of full circuits. Yet with that many stars moving that fast, the system stays stable. You do not get a giant demolition derby. That tells you the mass, the size and the gravity are all balanced in a very specific way. Andromeda is big enough and massive enough for 1 trillion moving stars to keep orbiting without chaos. So how does that compare to the tiny piece of space you live in around the Sun? In your local neighbourhood, if you draw a sphere 10 light years across, you only find a few dozen stars at most. The solar system lives in a fairly empty patch of the Milky Way, with big distances between neighbours. If you took that same 10 light year sphere and placed it in Andromeda's central bulge, the number of stars inside could jump to millions. Put your own solar system into that environment, and the night sky would change completely. There would be bright stars in every direction, many of them much closer than your current nearest neighbour, Proxima Centauri, which is about 4 light years away. The concept of a dark night, where the Milky Way band is a special feature, would basically vanish. The sky would be crowded and bright almost all the time. All of those stars add up to a huge amount of mass. If you take that trillion star figure and assume that on average each star has about half the mass of the Sun, which is a reasonable guess because there are many more low-mass stars than high-mass ones, you get a total of roughly 500 billion solar masses locked up in normal, baryonic matter. In metric, that is on the order of 10 to the power of 41 kilograms. That is mass you can, in principle, see or detect with normal light, from radio waves through optical to X-rays. And when astronomers model the way stars and gas move in Andromeda, these numbers line up well. The visible matter in stars explains a big chunk of the inner gravity. But here is the part where the stakes jump again. Even 500 billion solar masses in stars is not the whole story. When you look at how fast stars are orbiting in the outer disk, and how gas moves in the outskirts, you find that the visible matter alone is not enough to hold them in place. Something else, something invisible, has to be adding extra gravity. That something is dark matter. Once you include the dark matter halo, the total mass of Andromeda goes up to several times 10 to the power of 11, maybe close to 1 trillion solar masses. The bright familiar stars are only a fraction of the full weight of the galaxy. So you have a galaxy that is not just large in distance but large in star count, and even larger in total mass when you add the invisible component. And that raises a sharp next question. If Andromeda holds 1 trillion stars and a massive dark halo, how exactly is all of that material arranged? Where do the bulge, the disk, the gas and the halo actually sit? And what does that layout do to your idea of its real size? How do you even picture a galaxy that's not one simple thing, but a stack of different structures piled on top of each other? Start in the middle. At Andromeda's core, there's a central bulge a few thousand light years across, a dense ball of mostly older, redder stars. This is the part that blasts out most of the light in a normal photograph, the bright, almost circular glow in the centre. In this region, stellar densities spike hard. Instead of a few stars spread over several light years, you can get thousands of stars crammed into a single cubic light year. Their orbits are not the neat, flat circles you see in the outer disk. Paths crisscross in all directions, more like a swarm than a clean rotation. Buried inside that bulge is a supermassive black hole, with a mass on the order of 100 million suns. It doesn't take up much physical space, the event horizon is smaller than the orbit of Mercury, but its gravity anchors the very centre of the galaxy. When you talk about the middle of Andromeda, you're really talking about the point everything orbits around, set by that black hole and the mass of the bulge. If the bulge is the packed core, what happens as soon as you step just outside it? You hit the stellar disk, the huge flat component people usually mean when they say galaxy disk. In Andromeda, this thin disk stretches out to somewhere between about 150,000 and 260,000 light years in diameter, depending on how faint you're willing to follow the starlight. That is already much larger than the roughly 100,000 light-year disk you often see quoted for the Milky Way. Out here, motion becomes more organised. Stars follow relatively flat, ordered paths in a common plane, like lanes on a massive circular highway. Typical orbital speeds are around 250 kilometers per second, roughly 560,000 miles per hour. That is fast enough to go around Earth in a minute, but in Andromeda's gravity, it is just a comfortable cruising speed. The disk is where you find spiral arms, rings, and most of the ongoing structure that defines Andromeda's overall shape. but the stars are only half the story in that disk. So what's filling the gaps between them? Threaded through and around the stellar disk is a thicker disk of gas, mainly neutral hydrogen, plus molecular clouds where the gas is clumped together more strongly. Radio telescopes map this hydrogen far beyond the obvious bright starry regions, and very often the gas disk extends farther out than the visible stars. This gas is the raw material for new stars. Where it gets compressed, you see active star formation, hot, young blue stars lighting up regions of ionized gas called H2 regions. Those glowing patches, plus dust lanes, outline the spiral arms and rings. In other words, the gas disk tells you where the galaxy is still alive, in a star-forming sense, not just where old stars are coasting. It stretches Andromeda's functional size beyond the radius you'd pick from starlight alone. So if the bulge, stars and gas form the bright busy part, what's going on even farther out, where your eye sees nothing at all? Far beyond the main disk, there is a stellar halo, a very low-density extended component that reaches hundreds of thousands of light-years from the centre. You don't see it as a solid glow. Instead, with big telescopes, astronomers pick up individual red giant stars scattered across this region, and long tidal streams, faint ribbons of stars arcing around Andromeda. Those streams are the debris of smaller dwarf galaxies that Andromeda has pulled apart over billions of years. Their stars got stripped out and stretched along their orbits, leaving these ghostly structures behind. The halo has no sharp edge. As you move outward, the number of stars per unit volume just slowly drops, until the galaxy's stellar population becomes indistinguishable from the general background of the universe. This is the outermost visible footprint of Andromeda's growth history. When you put all of these pieces together, how can you possibly talk about one single seas and keep a straight face? If you stop at the bulge, Andromeda is only a few thousand light years across. If you define it by the bright stellar disk, you get something like 150,000 to 260,000 light years. If you use the gas disk, it reaches farther out again. Add the stellar halo, and you're talking about structures stretching several 100,000 light years. And if you then include the full dark matter halo that wraps all of this, you can push the effective size toward 1,000,000 light years. The galaxy is not a rigid frisbee with one clean radius. It is a layered gravitational system, with each layer extending farther and controlling space over a larger zone. Every new layer you include forces you to say, okay, it's bigger than I thought again. So you don't just ask how wide is Andromeda, you ask, where does the bright central bulge end? Where does the ordered disk dominate? Where does the gas still form stars? Where do the cannibalized halos of dead galaxies fade out? And where does the invisible dark matter stop ruling the orbits? And once you accept that structure, there's another step that raises the stakes even more, because that outermost structure, the dark matter halo, doesn't just extend far, it actually overlaps with the halo of the Milky Way, which means the real size of Andromeda might already be pressing into the space you live in. Here's the problem with trusting what you see in Andromeda. Almost all of the gravity is coming from stuff you can't see at all. If you take only the visible matter in Andromeda, the stars, the gas, the dust, and you plug that into normal gravity, you can predict how fast stars ought to orbit at different distances from the centre. Close in where there's a lot of visible mass, you expect high speeds. Far out where you see hardly any stars or gas, you expect those speeds to drop. That's what would happen in a simple system where most of the mass is concentrated in the middle. But when astronomers actually measure the rotation speeds in Andromeda, the curve stays flat. Stars tens of thousands of light years from the centre still move at around 200 to 250 kilometers per second, roughly 450,000 to 560,000 miles per hour. They do not slow down the way they should if only visible matter were pulling on them. That flat rotation curve is the red flag. It says very clearly, there is more mass out there than the things you can see. That extra mass is what we call dark matter. So how heavy is this invisible structure that's holding Andromeda together and boosting those speeds in the outskirts? astronomers talk about the virial mass of a galaxy, basically the total mass of everything gravitationally bound in its halo, including stars, gas, dust, and dark matter. For Andromeda, the best estimates cluster around a few hundred billion to about 1 trillion solar masses. Recent analyses tend to favour values towards the lower end, around 450 billion times the mass of the Sun. In metric, that's roughly 9 times 10 to the power of 41 kilograms. In plain language, that's the mass of hundreds of billions of suns, not in the bright disk alone, but spread out in an enormous, roughly spherical halo. Even if you pick the lighter estimate, you're still dealing with an object so massive that its gravity dominates a huge chunk of space around it. If that much mass is sitting in a halo, how far out does Andromeda's true gravitational reach actually go? Numerical simulations and observations suggest that Andromeda's dark matter halo could extend to something like 200 to 300 kiloparsecs from the centre. 1 kiloparsec is about 3,260 light years, so you're looking at a halo radius of roughly 650,000 to about 1 million light years. That's not the diameter, that's the radius. In diameter, you're talking close to 2 million light years of influence end-to-end for the full halo. At that scale, the dark matter halos of Andromeda and the Milky Way are not neatly separated bubbles. They may already be overlapping, blending into one larger shared structure. In terms of dark matter, these two galaxies are not just neighbours, they are cohabiting the same extended envelope of gravity. So where do the things you actually see fit inside this much larger invisible structure? All the familiar baryonic matter, the normal matter made of protons and neutrons, lives in a much smaller region. The luminous disk of Andromeda, stars plus most of the gas, sits inside roughly 100 to 130 kiloparsecs. That's around 300,000 to 400,000 light years. That bright part is like a small glowing coin sitting in the middle of a huge transparent sphere. Most of the stars you talk about, the spiral arms, the bulge, the obvious disk, are confined to the inner part. But most of the gravity, especially in the outer regions, comes from dark matter in the halo beyond the bright disk. That is why when you ask how big is Andromeda, the most physically honest answer is not 200,000 light years across. It's something like it controls space over a region about 1 million light years wide. That control, that gravitational reach, is the real footprint of the galaxy. What does it mean for you personally that galaxies are wrapped in overlapping dark halos instead of being clean, isolated islands? You live inside the Milky Way, and the Milky Way also sits inside its own dark matter halo, just like Andromeda. That halo doesn't stop where the visible disk ends, it extends far out into the surrounding space. When you consider both halos together, plus all the smaller galaxies around them, you get the gravitational structure called the local group. In that bigger system, Andromeda and the Milky Way are just the two biggest wells in a shared potential, both sunk into the same underlying dark matter web. The visible galaxies are like bright spots painted onto a much larger invisible scaffold. Once you start following where the gravity really comes from, instead of just where the light is, your everyday idea of size starts to fall apart. You're used to thinking in solid edges, clear borders, simple diameters. Dark matter doesn't care about that. It stretches out in smooth, extended halos. It overlaps between galaxies. It links groups of galaxies together. The universe is stitched together by these invisible structures, and the bright disks, including Andromeda's, are just thin decorations on top. So now you have a galaxy that's larger in stars than the Milky Way, wrapped in a dark halo that may already be blending with our own and affecting the future orbit of our entire system. That raises the next uncomfortable question. If Andromeda might not even be the clearly heavier one anymore, then in this shared dark matter environment, which galaxy is actually bigger? And what does bigger even mean when you put Andromeda head-to-head with the Milky Way? How do you decide who's bigger when two galaxies are both trying to claim the top spot? For a long time the story was simple. Andromeda is the big one, Textbooks, documentaries, planetarium shows all repeated the same line: Andromeda is bigger, brighter, and more massive than the Milky Way by something like 25 to 50%. Star counts, total brightness, rotation speeds, everything seemed to point the same way. Andromeda looked like the heavyweight in the neighbourhood, the big spiral that our own galaxy had to respect. You grow up with that idea, and it feels settled, like a basic fact. So what happens when new data starts quietly erasing that comfortable gap? Over the last years, better measurements and more advanced dynamical models have taken another look at Andromeda's total mass, especially its dark matter halo. Some of those newer results put Andromeda's mass at around a few hundred billion solar masses, with a lot of attention on values near 450 billion suns. That number is not dramatically larger than current estimates for the Milky Way. In some comparisons, Andromeda comes out similar. In others, it might even be a bit lighter. That flips the old story. The big bully next door might not be a giant towering over us. It might be more like a slightly larger or even roughly equal sibling. The confidence that Andromeda obviously wins on mass is gone. If the total mass is no longer a clear victory, does that mean Andromeda isn't really bigger at all? Not so fast. You have to separate how heavy from how far the visible stuff extends. When you look at the stellar disk, Andromeda still has the advantage. Its thin disk stretches somewhere between about 150,000 and 260,000 light-years in diameter, depending on how faint you're willing to trace the stars. The Milky Way's stellar disk is usually put around 100,000 light-years across. So in terms of pure visible span, how wide the bright component is, Andromeda still spreads out more. Stand outside both galaxies and just look at the light. Andromeda's disk covers a larger region. But if you zoom out to the scale of the dark matter halos, things get messy again. Halo sizes and total masses are harder to pin down than star counts, and the error bars are big. Some models give Andromeda a slightly larger halo, others give the Milky Way a comparable or even bigger one. Depending on which dataset and which modelling assumptions you trust, you can tell a story where Andromeda wins, or a story where it's a tie, or even one where the Milky Way quietly edges ahead. That's not a cop-out, that's just the current state of the measurements. When you hear someone say Andromeda is definitely more massive, that word definitely is doing a lot of unsupported work. So if the crown keeps sliding back and forth, what does bigger actually mean in the space we live in, the local group? On the scale of a few million parsecs, roughly 10 million light-years, the local group is dominated by three main players: Andromeda, the Milky Way, and the Triangulum Galaxy. Andromeda and the Milky Way are the two giants. Triangulum is a solid but clearly smaller third place, and everything else is a long list of dwarf galaxies orbiting around or falling into these big ones. The combined gravity of Andromeda and the Milky Way shapes the whole local group, defines which smaller galaxies stay bound, which ones get torn apart, and how the group as a whole moves relative to neighbouring groups and clusters. Whether Andromeda wins on mass by 20% or loses by 10% doesn't change the basic picture. It's still one of the two anchors of this region of the universe. Where the rivalry really matters is in how you explain size to yourself and to anyone listening. If Andromeda is not clearly more massive, then you can't just point at the mass number and say bigger, end of story. You have to be more precise. You can say, Andromeda has a larger luminous disk, it stretches farther in bright stars, it probably hosts more total stars, maybe around 1 trillion compared to a few hundred billion in the Milky Way. In that sense, in terms of raw star factory output and visible footprint, Andromeda is bigger. But in terms of dark matter halo size and total mass, the comparison is now closer to a tie, with uncertainties big enough that either galaxy could take the lead depending on which measurement you prioritize. That nuance is powerful because it shows you that bigger is not a single number, it's a choice. Are you talking about star count, disk diameter, halo radius, or virial mass? You can rank galaxies differently depending on which of those you care about. For a human looking up at the sky, the luminous disk and apparent size matter a lot. For orbital dynamics on million light-year scales, the total halo mass is what counts. For star formation history, you might care about gas content and current star-forming disk size instead. The Andromeda versus Milky Way rivalry forces you to say out loud which kind of big you mean. And once you start thinking that way, another question lands. If both galaxies have similar total masses, similar halo structures, and similar rotation speeds, what can Andromeda's spin, the way its stars and gas actually move, tell you about how its mass is distributed and how far that gravity really reaches? How do you tell how big something is? Just by watching how fast it spins. If you map how fast gas and stars orbit Andromeda at different distances from the centre, you get a rotation curve, speed versus radius. In a simple system where most of the mass is concentrated near the centre, you expect orbital speeds to drop as you move out. Farther from the core, weaker gravity, slower motion. That's what basic Newtonian gravity with a central mass predicts. But that is not what Andromeda does. When astronomers measure real speeds, they find that from the inner disk out into the outer regions, the rotation curve stays roughly flat. Stars and gas way out in the disk still move at around 200 to 250 kilometers per second, the same ballpark speed as material closer in. That is the classic signal that mass is not just piled up in the bright center, it extends far beyond the region where the visible light seems to die out. In other words, the effective size of Andromeda's gravity is much larger than the visible disk. So how long does it actually take for a star moving that fast to loop once around this galaxy-sized track? Pick a radius around 30,000 light-years from the center. At that distance, with orbital speeds of a few hundred kilometers per second, a single full orbit takes on the order of 250 million years. Go farther out, say around 100,000 light-years from the center, and that orbital period stretches toward 1 billion years. For context, the dinosaurs went extinct about 66 million years ago. Since then, a star at 30,000 light-years in Andromeda has not even finished a full orbit. At 100,000 light-years, it has barely started one. The galaxy is so big and the orbits are so long that entire eras of life on Earth happen, while a star in Andromeda moves through just a small fraction of its path. And yet the disk as a whole maintains its structure over billions of years. Spiral arms persist. The general rotation pattern stays intact. That tells you the gravitational well is deep and stable on timescales that make human history look like noise. So how do you turn those orbital speeds into an actual weight for the galaxy? Not just a vague sense that it's massive. Astronomers take the rotation curve and fit it with models that include 3 main components: the stars in the disk and bulge, the gas in the disk, and a dark matter halo around everything. Each component contributes to the total gravity at each radius. By adjusting how much mass you assign to each part and how that mass is distributed, you try to match the observed speeds at all distances. When you find a model that matches the real rotation curve, you can read off the mass profile, how much mass is inside 10,000 light-years, 50,000, 100,000, and so on. That is how you get total mass estimates for Andromeda, in the range of roughly 500 billion to about 1 trillion solar masses, and halo radii of hundreds of thousands of light-years, up to around 1 million. The key point is that you cannot fit the flat outer part of the rotation curve with stars and gas alone. You have to add a dark halo. Without that extended halo, the speeds would drop too fast as you move outward. The data simply refuse to cooperate with a light-only model. The rotation curve is practically shouting the gravity is still strong where the starlight is weak. How does Andromeda's spin compare to the Milky Way's? And what does that say about the scale of both systems? Both galaxies have rotation speeds in the same basic range, around 200 to 250 kilometers per second. To give that some intuitive meaning, a typical passenger jet flies at maybe 900 kilometers per hour, which is about 0.25 kilometers per second. So a star in the disk of Andromeda is moving around the center at something like 800 to 1,000 times the speed of a jet. A high-speed rifle bullet might travel around 1 kilometer per second, so we were talking a star moving at roughly 200 to 250 times that. These stars are cruising at speeds that in human terms are extreme, but in the context of a galactic gravitational well, they are just stable orbital velocities. The fact that gas and stars can move that fast over such huge distances without flying away into intergalactic space tells you the gravitational field they are trapped in is enormous. That is another way of saying the effective size of the mass distribution is huge, and this is where the whole question of how big is Andromeda suddenly blows up into something much larger than one galaxy. Rotation curves like Andromeda's are one of the main reasons we believe dark matter exists at all. When astronomers first mapped these curves for different galaxies, they kept seeing the same pattern, speed staying flat instead of dropping off. That forced the conclusion that most of the mass, and therefore most of the gravity, was coming from some invisible component extending far beyond the bright parts. When you measure how big Andromeda's gravity feels to its orbiting stars, you are not just answering a size question, you are helping rewrite the matter inventory of the entire universe. You go in asking, how big is this galaxy? And you come out with 85% of the matter out there is dark. We can only see a small fraction of what actually exists. So if the rotation of the outer disk already pushed you to accept that most of Andromeda's mass is invisible, what happens when you stop looking at the outskirts and point your attention right at the center, where a supermassive black hole is quietly warping space and defining the inner scale of the whole system? How do you talk about size when the most important thing in the galaxy is almost too small to see but dictates everything around it? Go right into the inner few dozen light years of Andromeda, and the environment there is nothing like your local space. In the solar neighborhood, you get a few stars spread over several light years. Near Andromeda's center, within a radius of just a few light years, you can pack in millions of stars. They are crammed together at densities orders of magnitude higher than what you're used to, all whipping around the center at hundreds of kilometers per second, hundreds of thousands of miles per hour. Space there is not empty background with one sun and a few faint neighbors. It's a real crowd. Every star feels the pull of many others, plus the pull of something much heavier buried in the middle. So what exactly is sitting at the heart of that crowded region, and how big is it really? Andromeda's central black hole is estimated to be around 100 million times the mass of the Sun. In terms of sheer mass, that's a monster. But in terms of physical size, it's surprisingly compact. The event horizon, the point of no return, is only a few 100 million kilometers across. That's less than the diameter of Mercury's orbit around the Sun, so on a solar system scale, it's still small. The catch is that this is not the relevant size for the galaxy. What matters is the sphere of influence, the region where the black hole's gravity dominates the motions of stars more than the rest of the bulge does. That zone stretches over light years, not just millions of kilometers. In that inner few light years, orbits are not set by the whole galaxy, they are set mostly by this one compact object. Here, size is about gravitational control, not about how wide the object physically is. If the central object is so small on the sky, how did astronomers even figure out that the core is more complicated than a simple bright point? High-resolution images of Andromeda's core from instruments like Hubble show that the nucleus is not a single clean brightness peak. Instead, you see what looks like a double nucleus, two close bright spots called P1 and P2. At first glance, that's confusing. You only expect one center. The best explanation is that these peaks are parts of a tiny stellar disk orbiting the black hole on eccentric paths, so you're seeing different clumps along those orbits, projected against each other. This asymmetric, lopsided structure spans just a few parsecs, a few light years, but it matters a lot because it tells you that stars near the black hole are not just randomly scattered, they're organized in a specific, unstable-looking configuration. That, in turn, affects how gas flows, how stars crowd together, and how the whole central kiloparsec behaves dynamically. With a black hole that massive, you might expect Andromeda's center to be blasting out energy like a quasar, so why isn't it lighting up the universe right now? Compared to active galactic nuclei in more violent galaxies, Andromeda's central engine is surprisingly quiet. It does produce X-rays and radio emission, but at a relatively low level. That tells you the accretion rate, the rate at which matter is currently falling into the black hole, is small. The potential power is huge. A 100 million solar mass black hole could, in principle, pour out staggering amounts of radiation if it were being fed a lot of gas at once. But right now, it's running on a very low fuel supply. So the size of its energetic influence, the region dominated by intense radiation and outflows, is much smaller than what it could be in a high accretion phase. You have a giant engine idling, not redlining. If the black hole is tiny compared to the galaxy and not even running at full power, why should it matter for Andromeda's overall size and structure? Even though the black hole is less than 1,000th of the total mass of the galaxy, its presence changes the rules in the inner region. Its gravity shapes orbits in the central bulge, influences whether a bar structure can form or stay stable, and helps set how gas flows inward through the disk. Gas that loses angular momentum and falls toward the center has to navigate that deep potential well, which affects where it piles up, where star formation is triggered, and where it is shut down. Over billions of years, that feedback between central mass, gas inflow, and star formation helps set the profile of the inner few kiloparsecs, the part of the galaxy that defines the bright core you see from far away. So even here, in the very middle, size is layered. There's the tiny physical size of the black hole, the larger sphere where its gravity dominates, the even larger region where it shapes the dynamics of the bulge and inner disk, and then the visible brightness profile built on top of all of that. The monster in the middle is a small fraction of the mass, but it decides how the innermost part of the galaxy is carved out. And once you've understood how that tiny central engine sculpts the core, the next question is obvious. How is the rest of the disk carved up? In rings, arms, and shock fronts? And what do those structures say about the real functional size of the part of Andromeda that is still actively forming stars? How do you measure a galaxy's size when the important parts are not just how far the light goes, but where the galaxy is actually busy building new stars? Look at Andromeda's disk in infrared and radio light, and you don't just see a smooth spiral. You see ring-like structures, big zones where star formation suddenly jumps. One of the most famous is the 10 kiloparsec ring. That's a ring about 10,000 parsecs, or roughly 32,600 light-years, from the center. There's another, more distant ring further out. These are not tiny features. Each ring is tens of thousands of light-years wide, and they stand out because that is where gas is being compressed and turned into new stars at a higher rate than the regions just inside or outside. Those rings act like built-in yardsticks. You can say, inside the 10 kiloparsec ring, conditions look like this. Outside it, they change. They give you concrete radii to talk about instead of just saying somewhere in the disk. So if there are rings cutting across the disk, what role do the spiral arms play in setting Andromeda's effective size? The spiral arms don't stop at some fixed sharp radius. They don't hit a wall and simply vanish. Instead, they gradually taper off, getting fainter and more diffuse as you move outward. But you can track individual arms for tens of kiloparsecs, tens of thousands of light years, by following where young, blue stars, star-forming regions, and dust lanes line up. These arms are not solid things moving through the disk. They're patterns, density waves moving through the gas and stars, compressing material as they pass. Wherever the density wave is strong enough, gas clouds get squeezed, collapse, and form clusters of new stars. If you map where those arms still trigger star formation, you get something more useful than just a nominal diameter. You get the functional size of the star-forming disk, the region where the galaxy is still actively building new stellar populations, not just coasting on old ones. In Andromeda, you can trace this active zone out to several tens of kiloparsecs before star formation drops off and the disk becomes more quiescent. What is pushing the gas into these rings and arms hard enough to keep star formation going at specific radii? Part of the answer is internal. the galaxy's own spiral density waves and bar-like structures, but part of it comes from outside, from interactions with Andromeda's satellite galaxies, like Messier 32 and Messier 110. When these smaller galaxies orbit through or near Andromeda's disk, their gravity tugs on the gas, setting up tidal forces. Those forces can send shockwaves through the gas disk. Where a shock passes, gas gets compressed, and compressed gas cools and collapses more easily. That can create arcs and ring-like features at particular distances from the centre, regions where the gas is denser and star formation is enhanced. So instead of thinking of size as a smooth featureless radius, you can talk about specific zones where the physics changes. Inside a certain radius, you might have stronger bars or different gas dynamics. At the 10 kiloparsec ring, you have a star-forming hotspot. Beyond a certain radius, shocks from interactions become weaker, gas thins out, and new stars become rare. The galaxy's disk is not uniform. It's structured by these interactions and waves, and those structures are stamped at very specific distances. How does this compare to where you're sitting right now in the Milky Way? The Sun orbits about 8 kiloparsecs, roughly 26,000 light-years, from the centre of the Milky Way. That puts us somewhere in the inner half of our galaxy's stellar disk. Not right in the core, not in the extreme outskirts. If you take that same galactocentric radius, 8 kiloparsecs, and drop a hypothetical solar system into Andromeda at that distance from its centre, you end up relatively more inner disk compared to its larger overall size. Andromeda's disk stretches farther out than the Milky Way's, so being 26,000 light-years from its centre puts you proportionally closer in. At that position, your sky could easily be richer in bright spiral arm features. You would likely be sitting in or near one of the stronger arms or rings with more massive star-forming regions nearby, more luminous young clusters, and more visible structure in the band of the galaxy. Your night sky wouldn't just show a milky band, it could be cut through with bright knots and lanes from neighbouring star-forming complexes, simply because the real estate for arms and rings is extended and denser at that scaled radius. So if you stop pretending the whole disk is equal, and instead ask, where is the galaxy still building new stars, still forming planets, still updating its inventory of possible habitable systems? What size do you get then? If you define a useful galaxy size as the zone where gas is still actively forming stars, Andromeda's star-forming disk runs out to roughly 20 to 30 kiloparsecs from the centre, so about 65,000 to 100,000 light-years. Inside that zone, gas is dense enough and disturbed enough by waves and interactions to keep making new stellar systems. Outside it, the disk exists, stars are there, but the gas is thinner, colder and less active. Star formation slows down or almost stops, and you effectively move into a more fossil-like part of the galaxy. That means the life-bearing potential of Andromeda, in the sense of where new planetary systems are still being built and where you might get fresh generations of stars with heavy elements needed for complex chemistry, occupies a radius smaller than the full luminous disk, and much smaller than the full dark halo. But it is still huge in human terms, on the order of 100,000 light-years across, a zone that large, packed with billions of stars and countless planets, is the real active area of the galaxy. So when you think about Andromeda's size not just as a number, but as a footprint of where interesting things can happen, you end up with yet another answer, the size of the star-forming real estate. And that naturally leads to the next question. If you actually lived inside that disk at one of those radii, what would Andromeda feel like on a human scale? How would your everyday sense of distance, travel, and even communication collapse under those numbers? How would everyday life even make sense if you actually lived inside Andromeda, instead of just staring at it from far away? Start with your neighbourhood on a scaled-down map. Take Andromeda's disk and shrink it until it's the size of a large country, around 3,000 kilometres across, roughly 1,860 miles. On that map, your entire solar system, from the Sun out past the outer planets, would shrink to something like a grain of sand a few centimetres across. The nearest star, Proxima Centauri, would be another grain of sand sitting maybe a meter away. The distances that feel huge to you now, like the jump from Earth to Mars, would barely register on that map. They'd be microscopic wiggles inside one tiny patch of one spiral arm. All of human exploration, crossing oceans, flying around the world, even sending probes to the edge of the solar system, would reduce to a short walk across a tiny part of that country-sized disk. On Andromeda's scale, your entire history of reaching far is a step and a half. So if the map shrinks your proudest journeys down to a couple of footsteps, what happens when you try to move around this galaxy at real physical speeds? Take the fastest spacecraft humanity has ever launched. Things like the Parker Solar Probe, which can reach speeds around 70 kilometers per second, roughly 43 miles per second when it slingshots close to the Sun. That is insanely fast by human standards. At that speed, crossing just 1 light year would take something like 19,000 years. That's older than civilization. To get across even a modest fraction of Andromeda's disk, say tens of thousands of light years, you're deep into time spans that make recorded history vanish. Now be generous and give yourself a speed similar to a typical star in the disk, around 250 kilometers per second, about 560,000 miles per hour. Even then, to cross a disk on the order of 150,000 to 260,000 light years, you are talking hundreds of millions of years. That is geological time, evolutionary time, not mission length time. Human attention, human planning, and none of it can stretch that far. Galaxies operate on timescales where even a full orbit is something no civilization will ever personally witness from start to finish. If physical travel is that hopeless over galactic distances, could you at least talk across the disk in a useful way? Even if you push communication to the absolute limit, using light itself, you still lose. A radio signal, which travels at the speed of light, would take on the order of 150,000 to 260,000 years to go from one side of Andromeda's disk to the other, depending on which diameter you pick. That's just one way. A round-trip hello and got your message can easily be 500,000 years. Entire species could evolve, flourish and disappear on a planet in one sector of the disk before their message even reaches someone on the opposite edge. So the idea of a real-time galactic internet where civilizations across Andromeda chat, argue, and stream videos in sync is basically dead on arrival. Even a slow forum where you expect a reply within 1,000 years is optimistic. Communication delay is not a technical glitch you fix with better bandwidth. It's baked into the structure of space and the size of the galaxy. If you can't move fast enough and you can't talk fast enough, what actually defines neighborhood and structure inside a galaxy this big? The answer is gravity layered over and over. Planets sit in the gravity wells of their stars. Those stars orbit inside the gravitational well of the stellar disk and bulge. The disk itself is wrapped in the deeper well of the dark matter halo. And that halo is one well inside an even larger one, the gravitational potential of the local group, which includes Andromeda, the Milky Way, Triangulum, and countless dwarfs. You're not just living in a big space, you're living inside a hierarchy of gravity wells nested inside each other. Size in this context stops being just how far from edge to edge, and becomes how many layers of orbits can you stack and still keep the system stable. If planets can orbit stars for billions of years without getting ripped away, if stars can orbit the galactic center repeatedly without the disk flying apart, if galaxies can orbit within a group without instantly merging, that tells you something about how deep and wide those gravitational wells are. Andromeda is big not only because it spans hundreds of thousands of light years, but because it holds together that stack of nested orbits over cosmic time. When you pull all of that together and try to compare it to anything human, your normal sense of speed and distance basically breaks. Your entire technology stack is tuned to a world where fast means a few kilometers per second. A rocket going into orbit might hit 8 or 10 kilometers per second, around 5 to 6 miles per second. Interplanetary probes push that a bit, maybe tens of kilometers per second. Those numbers feel extreme, they stress our engineering, they're at the edge of what current materials and fuels can handle. But Andromeda doesn't notice any of that. On galactic scales, speeds below hundreds of kilometers per second barely register. Distances below thousands of light years are local trivia. The structures that define the galaxy, from spiral arms to halos, are built on tens of thousands to millions of light years, and on timescales of hundreds of millions to billions of years. That mismatch is the core reason your intuition fails so hard when you think about how big Andromeda is. Your brain evolved to deal with hills, cities, maybe planets if you stretch it. It did not evolve to deal with a system so huge that crossing 1% of it at your fastest possible speed would still take longer than your species has existed. And once you understand that your tools for thinking about scale, speed, and communication don't work here, a final question starts to loom. If galaxies like Andromeda are this big, this massive, and this slow to change on human terms, what does it actually mean when you say the Milky Way and Andromeda might collide? And how big is Andromeda as a target in that future encounter? How big is Andromeda really, if what you care about is not just its width, but how hard it can hit us in the future? For a long time, the story was clean and scary. The Milky Way and Andromeda are on a collision course. They'll smash together in about 4 or 5 billion years, and you'll get a new merged system people like to call Milkomeda. That line showed up everywhere. It sounded inevitable, like a train on a track. But as better data came in from Hubble and Gaia, and people ran more detailed simulations with updated positions and proper motions, the clean story broke. The new models say that within the next 5 billion years, the odds of a full direct merger are actually very low, under a couple of percent. Stretch the timeline to 10 billion years, and the probability rises. Roughly 50 to 50 that a true merger happens in that window. So now the future is not guaranteed crash, it's maybe a glancing interaction, maybe a long messy dance, maybe a delayed merger much later. The trajectory is still being refined, and the system is more complex than the old one-sentence prediction. Once you drop the idea of a simple scheduled impact, the next question is, what does size even mean in this context? What exactly is Andromeda presenting as a target? For galaxy encounters, what matters is not just the bright disk diameter, it's the effective cross-section of all the mass that can interact, especially the dark matter halos. Andromeda's halo and the Milky Way's halo each reach out to hundreds of thousands of light years, maybe close to 1 million. When two halos that large overlap, you don't just have two neat disks passing by each other, you have two extended gravitational fields blending together. The stars themselves are still tiny points in a huge volume, and most will miss each other by huge margins. But their orbits do not ignore the combined pull. Even without a perfect head-on smash, once the halos interpenetrate, orbits start to shift, angular momentum is exchanged, and the overall shapes of both galaxies begin to distort. The size that matters here is the region where each galaxy's gravity significantly alters the paths of stars and gas in the other, and that region can be hundreds of thousands of light years across. So in a galactic collision, what's actually happening to the stars themselves, and how can something be so violent without being a literal pile-up? Even in a direct hit, where the disks line up badly and pass through each other, the chance of two individual stars physically colliding is tiny. Stars are small compared to the distances between them. Think of grains of sand separated by kilometers. You can overlay two such clouds and hardly any grains will touch. What really changes is the gravitational landscape. As the galaxies interpenetrate, stars feel rapidly changing tidal forces. Their orbits get stretched, twisted, and redirected. Some get flung out into long tidal tails. Some sink deeper into the merged core. The gas behaves differently. Gas clouds are extended, they fill space more smoothly, and when disks overlap, gas from one galaxy slams into gas from the other. Those collisions create shock fronts, compressing gas, heating it up, and then letting it cool and collapse. That's what triggers starbursts, intense phases of star formation lighting up the colliding system. At the same time, the central black holes in each galaxy start to spiral toward each other as dynamical friction drains their orbital energy, eventually merging into an even more massive black hole. So the big part of a collision is not the physical size of individual stars, it's the huge volume over which orbits are completely reshuffled, gas is shocked, and the internal structure of each galaxy is rewritten. If the future of the Milky Way Andromeda system is so uncertain, what controls how fast this all plays out? Or whether a full merger happens at all? The key factors are the sizes and masses of the dark matter halos, the initial relative velocities, and the presence of other massive players in the local group, like the large Magellanic Cloud orbiting the Milky Way. Those added masses and motions change the overall momentum and energy budget of the system. If the halos are heavier and more extended, their mutual gravity can pull the galaxies together more efficiently and over longer distances, shortening the merger timescale. If the initial tangential speeds are higher, the galaxies might swing past each other on long, looping orbits and only merge after several passes, or in extreme cases, not at all within the current age of the universe. When astronomers talk about a merger happening within a Hubble time, roughly the age of the universe, about 13.8 billion years, they're effectively using the collision timescale as a diagnostic of size and mass distribution. A system where two big halos pull together quickly tells you the halos are massive and the orbits are tightly bound. A system where they take longer than the age of the universe to merge suggests weaker binding or different initial conditions. So the billions of years clock on a possible Milky Way Andromeda merger is not just a prediction, it's a measurement of the effective size and weight of the whole setup. And that leads to the deeper point at this scale. Size isn't just a geometric detail, it's destiny. Galaxies as massive as Andromeda and the Milky Way don't just sit forever in perfect isolation. Their dark matter halos, their motions through the local group and their interactions with satellites make long-term rearrangement unavoidable on cosmic timescales. They may merge cleanly, they may undergo repeated close passes that strip stars and gas. They may drag in and consume smaller companions first, changing their mass and shape before they ever fully merge with each other. The exact path depends on the detailed mass distribution and initial velocities, but in every case the large-scale structure of the local group evolves because these halos are big, extended, and mutually influential. So when you ask, how big is Andromeda? In this context, you're not just asking for a diameter, you're asking, over how large a region does this galaxy set the future orbits, mergers, and transformations of everything around it? Size becomes another word for long-term fate. And once you zoom back out from this one future interaction and look at Andromeda in the context of all galaxies, the next logical question is, where does it sit on the cosmic size chart? Is it actually a true giant, or just one more mid-tier galaxy in a universe filled with even more extreme monsters? How can Andromeda feel impossibly huge to you and still count as nothing special to the universe? On the cosmic size chart, Andromeda is big, but it's not the top boss. It's what astronomers call an L-star, or L-spiral galaxy, basically a typical bright spiral around the knee of the galaxy luminosity function. In plain terms, it's a representative member of the common large galaxy crowd. There are galaxies out there, especially giant ellipticals in the centres of rich clusters, that are much more massive and much larger. Those giants can extend over several 100,000 light-years, with multiple times Andromeda's stellar mass, and even heavier dark matter halos. So yes, Andromeda is large, but in a room full of true monsters, it's just a big healthy spiral, not the extreme outlier. That doesn't mean Andromeda is small, it just means the universe's scale is brutal. If you look at galaxy surveys, things like the Sloan Digital Sky Survey, most of the galaxies you see are not huge spirals like Andromeda. They're dwarfs, small irregulars, modest spirals, systems with far fewer stars, smaller disks, and less massive halos. In terms of stellar mass and disk diameter, Andromeda sits well above the median. A disk in the 150,000 to 260,000 light-year range, and a stellar mass around a few 100 billion suns put it comfortably in the large category. Its dark matter halo, stretching up to hundreds of thousands of light years and totaling a few times 10 to the 11th power to about 10 to the 12th power solar masses, is typical for a massive galaxy living in the field, not in the crowded core of a rich cluster. So if you compare Andromeda to the full population of galaxies, it's bigger than most but smaller than the real top-end cluster centrals, mid-tier among giants, high-end overall. Why does that middle position matter so much to cosmology? Because you don't just have one L galaxy nearby, you have two, Andromeda and the Milky Way, sitting in the same small group. That makes the local group an extremely useful testbed. In your simulations of structure formation, you start with tiny density fluctuations in this early universe and let gravity grow them over 13.8 billion years. If your model is any good, it should naturally produce pairs of halos with masses of order 10 to the power of 12 solar masses, separated by a few hundred kiloparsecs, roughly a million light years, by the present day. If your simulation never creates a Milky Way Andromeda style setup, something in your physics, your dark matter model, or your initial conditions is off. The existence and properties of Andromeda are not just trivia. They're a hard constraint on how structure in the universe builds up from small scales to large. So how does a galaxy like Andromeda actually grow into its current size over cosmic time? It doesn't just puff up smoothly, it eats. Over billions of years, Andromeda has merged with and accreted smaller galaxies, mostly dwarfs, and pulled in gas from its surroundings. Each time a small galaxy gets too close, tidal forces strip its stars, stretch them into long streams, and eventually mix them into Andromeda's halo. When you look at the outskirts of Andromeda and see those faint tidal streams and shells, you're looking at fossils of that process. Each stream is a record of one more galaxy that no longer exists as a separate object. The extended stellar halo, which can reach hundreds of thousands of light years from the center, is basically a graveyard of these past mergers. The current size of Andromeda's stellar component, its thick halo plus its big disk, is the integrated sum of everything it has accreted, plus the stars it formed from gas it drew in. The dark matter halo tells a similar story, grown step by step as small halos fell in and merged. So when you say this is how big Andromeda is now, you're really describing the end result of 13.8 billion years of continuous growth, collisions, and cannibalism. Put that next to your own sense of scale, and the contrast is sharp. From your point of view, Andromeda is almost impossibly large, a disk up to a couple 100,000 light years across, a dark halo possibly pushing toward 1 million light years in effective radius. On top of that, around 1 trillion stars, each one with its own potential planetary systems, distances in light years, radii in hundreds of thousands of light years, velocities in hundreds of kilometers per second. No human technology, no vehicle, no signal delay you're used to dealing with prepares you for that. From the universe's point of view, Andromeda is a fairly normal large spiral in a quiet little group, not sitting in a massive cluster core, not firing off as a hyperactive quasar, not dominating a huge supercluster node. It's big enough to be important, common enough to be representative. That mismatch between this blows your mind and this is statistically ordinary is the real clue about cosmic scale. It tells you that your sense of big and small, built on kilometers and hours and lifetimes, is tuned to a tiny corner of what's possible. On the scale where Andromeda lives, those units barely register. And that brings you back to the starting question in a sharper way. If Andromeda is both huge to you and ordinary to the universe, and if every new observation keeps pushing its edges outward or revising its mass, is there any hope of ever getting a final fixed answer to how big is it? Or is that size itself a moving target that changes every time our instruments and models improve? How do you measure something when every time you look at it more closely, it gets bigger and more complicated? That's the problem with Andromeda right now. Every new survey, every new telescope redraws the map. As sensitivity improves, astronomers keep finding more structure around it, faint outer halos, ultra-diffuse satellite galaxies, and long thin stellar streams wrapping around the main disk. Things that were completely invisible a couple of decades ago now show up as real components of the system. Wide-field survey telescopes, scanning large chunks of sky with deep exposures, don't just tweak the distance and mass numbers, they change the actual shape and extent of what we call Andromeda. The outer halo stretches further, the list of satellites grows, the footprint of the galaxy on the sky gets more detailed. Every time the detectors get better, the official edge of Andromeda has to move, and so how do you turn this growing cloud of structures into something you can actually weigh and model instead of just a prettier picture? This is where ESA's Gaia mission comes in. Gaia measures positions and motions of stars with insanely high precision, down to micro-arc seconds. That's like seeing a coin on the moon shift by a few millimeters. For Andromeda, Gaia can measure proper motions of some of its stars and, crucially, of its satellite galaxies. Those faint companions orbiting around Andromeda are test particles in its gravity field. By tracking how they move on the sky over years, you can reconstruct the true three-dimensional velocities of these objects. Once you know how fast satellites are moving and how far they are from Andromeda's center, you can work backwards to the mass distribution that would keep them bound. Too little mass and they should escape. The fact that they are still in orbit tells you Andromeda's halo must be deep and extended enough to hold them. This lets astronomers refine estimates of the total mass and the size of the dark matter halo, beyond what rotation curves alone can do. So Gaia isn't just making a star catalogue, it's drawing the gravitational contour lines around Andromeda. But motions alone don't tell you the full story of how the galaxy is built inside that halo. So what fills in the rest? On the imaging side, Hubble has already pushed deep into Andromeda's disk and halo, resolving individual stars down to very faint magnitudes over large areas. Those stars are not just points, they're data points about the galaxy's history. Their colours and brightnesses tell you their ages and chemical compositions. Infrared observatories like JWST go a step further, pushing through dust-obscured regions that block visible light. In infrared, you can see stars that are hidden in optical images, and you can measure their properties in zones that were basically blacked out before. By combining these deep, multi-wavelength views, astronomers can map which parts of Andromeda are older, where the stellar populations are younger, where the stars are more metal-rich or metal-poor, and where distinct merger events have left behind specific groups of stars. That lets you define functional zones within the galaxy, not just by radius, but by history. Inner bulge built early, certain rings and arms dominated by younger stars, halo regions assembled from specific cannibalized dwarfs. The size of each zone becomes another dimension in how you talk about the galaxy's structure. Even that still treats the galaxy as a picture plus some velocities. So how do you turn it into a full 3D, physics-loaded map? That's where the ground-based giants and integral field spectrographs come in. The next generation of 30-meter class telescopes will collect huge amounts of light from small patches of Andromeda and split it into thousands of spectra at once. Integral field spectroscopy means that instead of one spectrum per object, you get a grid of spectra across a region. For each tiny patch, you can measure how fast stars and gas are moving toward or away from you, and what their chemical fingerprints look like. So instead of a single number like Andromeda is X light years wide, you start to say things like, this ring at 12 kiloparsecs is rotating at Y kilometers per second, and its stars are enriched in heavy elements to this level. Or, this tidal stream in the outer halo has stars with these specific chemical signatures, so it likely came from a dwarf galaxy with this kind of history. Size stops being a single radius and turns into a multi-dimensional data cube. Radius, thickness, velocity, metallicity, age. Each radius has its own velocity field, its own chemistry, its own formation story. With all of that power, is there any hope of finally nailing down a clean outer boundary? Or does Andromeda's edge just keep leaking away into the dark? Even with space telescopes, 30-meter mirrors and long surveys, you never reach a perfect absolute cutoff. There will always be stars below your current detection limit. gas at densities below your noise floor, and parts of the dark halo only indirectly constrained by motions on even larger scales. You can tighten the error bars, you can push the known halo farther out, you can detect fainter satellites and streams, but you will always have the suspicion that there is more just beyond your reach. As soon as you extend your sensitivity, you find something new. That's why Andromeda's size is fundamentally a moving target. It is not just that our numbers change because we were sloppy before, it's that the galaxy literally has no sharp edge. Our instruments keep getting better at telling us, no, it reaches further than that. There is more mass, more structure, more history out there. What counts as the galaxy grows as your tools improve, so you end up in a strange position. The more precisely you measure Andromeda, the harder it becomes to answer the original simple question with one neat figure. Every upgrade adds another radius, another mass layer, another kind of big. And that leaves one last step to take after all these methods, numbers, and structures, when someone finally corners you and asks, so how big is the Andromeda Galaxy really? What exactly do you say, and how do you turn this entire moving layered picture into an answer that doesn't lie, but also doesn't take an hour to explain? So after all of this, if someone corners you and says, seriously, how big is Andromeda? What do you actually say without starting a 40-minute lecture? You hit them with the quick fire numbers, no hesitation. You say, Andromeda's stellar disk is somewhere between about 150,000 and 260,000 light years across. That's roughly 1.4 to 2.5 quintillion kilometers, a 1 followed by 18 zeros. You say it has around 1 trillion stars, give or take a few hundred billion, so roughly 3 to 5 times the Milky Way's star count. You say the total mass, once you include dark matter, is in the range of a few hundred billion to about 1 trillion solar masses. So think on the order of 10 to the power of 41 to 10 to the power of 42 kilograms. And you say the dark matter halo, the real gravitational footprint, may extend to something like 1 million light years across. If they want miles, fine. That stellar disk is on the order of 1 quadrillion miles wide, and the halo pushes you towards several quadrillion. That set of 4 numbers already tells you this thing is way beyond anything your day-to-day units are built for. But for a video like this, that one-line answer is not enough. Because how big is not actually one question, it's 4 different questions hiding under the same words. You don't pretend there is a single Andromeda. You spell out 4 versions. First, the bright Andromeda, the stellar disk, the part you see in normal images, the thin rotating wheel of starlight stretching around a couple 100,000 light years across. That's the galaxy most people think of. Second, the gaseous Andromeda, the neutral hydrogen and molecular gas wrapped around and beyond that disk, mapped in radio and infrared, setting the radius where star formation is still actively happening. That version is bigger than the pure, what you see in visible light definition. Third, the stellar halo Andromeda, the faint outskirts full of red giants and tidal streams from shredded dwarf galaxies, reaching hundreds of thousands of light years out with no sharp edge, just a slow fade into the background. And finally, the dark matter Andromeda, the full virial radius of the halo, where its gravity still dominates, pushing the effective size toward that million light-year scale. All 4 are real. All 4 describe the same system from different angles. Each one breaks a different part of your intuition. Once you hold those 4 in your head, your sense of where you fit in the story changes pretty hard. You live in a galaxy that's roughly Milky Way sized, embedded in its own dark matter halo. That halo is probably already overlapping with Andromeda's halo. So you're sitting in a shared dark matter megaplex with a neighbour whose bright disk stretches hundreds of thousands of light years and whose gravity reaches roughly 1 million. Inside that combined structure, your entire observable human story, from the first cities to space telescopes, plays out in a region smaller than a rounding error in one spiral arm. Your whole history fits into a tiny patch that a galaxy simulation might treat as a single pixel. You worry about far, as in another continent or another planet. On Andromeda's scale, that's noise. And the real twist is that the more seriously we try to answer this size question, the less stable the answer becomes. Every time we upgrade our tools, our picture of Andromeda's size shifts. A new telescope goes online, and suddenly the halo is more extended than we thought. A new dynamical model drops, and the mass estimate moves, sometimes down, sometimes up. A deeper survey finds ultra-faint satellites and longer stellar streams, and what we thought was the outer edge turns out to be just another layer. Our idea of edge keeps failing basic reality checks. We learned that the visible disk is only part of the story, then that the gas extends further, then that the stellar halo extends further again, then that dark matter extends beyond all of that. Even our old Andromeda is definitely much more massive than the Milky Way line had to be revised. The galaxy forces us to keep raising the bar on what we mean by size, by mass, by edge. So when you finally come back to the question that started all of this, how big is the Andromeda Galaxy? The honest answer is not a neat diameter. It's a kind of surrender. Andromeda is big enough that your language starts to crack. Big enough that kilometers and miles feel like children's toys. Big enough that your own galaxy stops looking special and starts looking like just another bright patch in a much larger web. In strict numbers, yes, you can have to say a couple 100,000 light years in stars, up to 1 million in gravity, 1 trillion suns, a few 100 billion to 1 trillion solar masses. But the deeper answer is that Andromeda's true size is the gap it opens up between what your brain thinks big means and what the universe quietly does all the time. It's as large as the hole it tears in your sense of scale. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.